Imagine it is 3 a.m. and your production system is melting down. There is no database crash and no obvious bug in the logic. Instead, you are witnessing a silent cascade failure. In modern microservice architectures, we often see a single client request triggering a chain of 7 or 8 sequential REST calls across different services. Each jump adds TLS handshake, overhead, heavy JSON serialization, and HTTP 1 head-of-line blocking. When the auth service slows down by just 200 milliseconds, the entire request chain hits a timeout, and your thread pools saturate instantly. This is what I call the invisible performance killer. Many senior architects fall into the trap of choosing REST by default because it is familiar, ignoring the compounding latency of deep service meshes. We aren't just talking about milliseconds here. We are talking about system-wide instability caused poor protocol choices. By the end of this lecture, you will know exactly how to diagnose these bottlenecks and replace them with the right communication pattern. But first, let's look at the sheer scale of the efficiency we are leaving on the table right now. In my experience reviewing high-traffic architectures, simply switching the internal communication protocol can reduce latency by up to 70% without changing a single line of business logic. But this isn't just about speed. It is about systemic efficiency and developer sanity. As an architect, your promise to the organization isn't to use the coolest tech, but to ensure the system is resilient and maintainable. In 2026, the boundary between REST, GraphQL, and gRPC has blurred, yet the fundamental trade-offs remain. We are going to build a protocol strategy that cuts through the hype. We will look at how to move away from chatty APIs that waste bandwidth and move toward chunky or streamed interactions that maximize throughput. If you understand the underlying transport mechanics, you can design systems that handle 10 times the load with half the infrastructure cost. This lecture is your guide to making those high-stakes decisions with confidence. Does this sound like a tall order? I will show you exactly how the math works out in real-world scenarios. But wait, before we optimize, we must understand the true cost of our current mistakes. Let's talk about the data waste problem. In a typical REST environment, you often face the overfetching and underfetching dilemma. Your mobile app needs just the username and profile picture, but your user's View1 profile endpoint returns 50 fields, including addresses, purchase history, and metadata. That is 2 KB of data when you needed 100 bytes. Multiplied by 1 million concurrent users, and you are paying for massive bandwidth waste. Conversely, underfetching leads to the N+1 problem. To render a simple order list, the course first calls the order's API, then makes 20 separate calls to the product API to get the names and thumbnails. This redundancy creates massive network round trips that kill the user experience. These aren't just minor inefficiencies. They are architectural flaws that lead to higher cloud bills and slower mobile performance on weak networks. Seeing this visualized makes it clear why a one-size-fits-all REST approach is no longer viable for complex front ends. But is data the only thing we're wasting? Not even close. We're wasting something much more expensive: developer time. Beyond performance, there is the hidden labor cost of API maintenance. If you've ever spent 3 days tracking down a runtime error only to find out a field in a JSON response changed from an integer to a string, you've felt this pain. REST is fundamentally weakly typed at the contract level unless you meticulously maintain OpenAPI or Swagger docs. But let's be honest, in the heat of a sprint, documentation is the first thing to rot. This documentation debt leads to fragile integrations and constant friction between front-end and back-end teams. Compare this to gRPC or GraphQL, where the schema is the single source of truth and type safety is enforced by the compiler or the query engine. Choosing the wrong protocol means signing up for a lifetime of manual documentation and Slack-based debugging, where developers constantly ask, "What does this API return again?" As an architect, your job is to reduce this cognitive load. We need a framework that moves us from accidental architecture to intentional choices. But how do we decide which trade-off to accept? This brings us to the core philosophy of a professional engineer. In the world of information processing professional engineers, we have a saying: architecture is not about finding the perfect tool. It is about choosing the least worst trade-off for your specific constraints. There is no such thing as a best protocol. REST is excellent for public APIs because of its ubiquity and catching. gRPC is king for internal microservices because of its raw speed and strict contracts. GraphQL is a godsend for complex frontends that need to aggregate data from multiple sources. The trap senior architects fall into is golden hammer syndrome, trying to use their favorite tool for every problem. To avoid this, we use architecture decision records, or ADRs, to document why we chose a specific trade-off at a specific time. In this lecture series, I'm to give you the decision matrix I use to evaluate these protocols based on latency, throughput, developer experience, and system constraints. This isn't just theory, it is a battle-tested framework for 2026. Ready to see the actual paradigms that drive these decisions. In the next chapter, we dive into the 3 core models: resources, graphs, and functions. Most developers think they're building RESTful APIs just because they put nouns in their URLs, but in reality, they're just doing HTTP-based or PC. True REST is about resources and constraints. When we talk about statelessness, it means the server shouldn't have to remember who you are between requests. Every single call must contain all the information needed to understand it. This is why REST scales so well horizontally. Then there's the uniform interface, the idea that if you know how to interact with one resource, you know how to interact with them all using standard HTTP verbs like GAT, POST, and DELET. This predictability is what made REST the gold standard for public-facing APIs, where you don't control the client. But let's be honest, how many of you actually implement HTTPS? Almost no one. This gap between the academic definition and the pragmatic REST we use today is where the first design mistakes happen. However, ignoring these constraints leads to a brittle system that breaks the moment your traffic spikes. Do you really understand the cost of breaking statelessness? I'll show you the architectural price tag in the next scene. If you want to move from a junior to a senior architect level, you need to master the Richardson maturity model. Most internal APIs are stuck at level 2, simply using HTTP verbs correctly. But the real power of REST reveals itself at level 3 with HTTPS, or hypermedia, as the engine of application state. It sounds academic, but it's about discoverability. More importantly, real REST architects leverage the HTTP protocol itself for caching. Are you using EDAGs and if modified since headers? In a global system with high egress costs, these headers are the difference between a massive cloud bill and a lean operation. When a CDN can serve a 304 not modified response instead of a full 200 OK with a heavy payload, your system's latency drops and your wallet stays full. But wait, while REST is great for the public web, it starts to fall apart when we move to the internal service mesh. This is where the verbosity of JSON and the lack of strict typing begin to hurt. But is it really as bad as they say? Let's look at the friction points directly. In a modern microservices environment, REST often becomes its own worst enemy. Think about a typical JSON payload. You're sending the same field names like user ID or transaction timestamp as plain text over the wire millions of times. That's pure overhead. Then there's the problem of overfetching, where you just want a user's name, but the API forces you to download their entire profile, including addresses and order history. But the silent killer is the lack of a strict contract. OpenAPI is great, but it's often an afterthought. If a producer changes a field from an integer to a float, and the consumer doesn't know, your system fails at runtime, not compile time. This weak typing at the network layer is why technical debt accumulates so quickly in REST-heavy internal systems. We need something that provides both efficiency and safety. Does such a thing exist? Well, two major challengers have entered the ring to solve exactly these problems. One handles the complexity of the front end, and the other handles the raw performance of the backend. Let's see who they are. GraphQL is essentially the query language for your API. It was born out of the need to solve the mess of the mobile front end, where bandwidth is precious and latency is high. Instead of the server deciding what the client gets, the client tells the server exactly what it needs. This makes it the absolute king of the backend for front-end or BFF layer. You define a schema, and the front-end can query across multiple resources in a single trip. No more N+1 request problems where you fetch a list and then have to fetch details for every item. But here's the senior insight. GraphQL doesn't magically make your backend faster. In fact, it can make it slower if you aren't careful with your resolvers. You've essentially handed SQL-like power to the client, and if they send a deeply nested query, they can bring your database to its knees. It's a trade-off, front-end flexibility versus back-end complexity. But is flexibility what you need for internal service communication, or do you need raw, unadulterated speed? That's where our next challenger comes in. While GraphQL conquers the UI, gRPC is the powerhouse for internal service-to-service communication. It's built on HTTP2, which is a massive game changer. Unlike HTTP 1.1 used by most REST implementations, HTTP 2 allows for multiplexing, meaning multiple requests can happen over a single connection simultaneously without waiting for the previous one to finish. And the data, it's not human-readable JSON, it's binary protocol buffers. This means the payload is incredibly small and the serialization speed is lightning fast because the CPU doesn't have to parse strings into objects, it's just bytes. If you're building a high-throughput microservice architecture where services talk to each other thousands of times a second, gRPC is your best friend. It also supports bidirectional streaming natively, which is a nightmare to implement in REST. There's a catch: it's hard to debug with simple tools like QRL because you can't read the binary data. So you're trading human readability for machine efficiency. But wait, there's another reason gRPC is winning the war in the backend, and it's all about the contract. In 2026, the biggest risk in a large-scale system isn't performance. It's developer productivity and system reliability. This is where gRPC and GraphQL win over REST. They are schema-first by design. In gRPC, you define your service in a proto file. In GraphQL, you have your schema definition. These aren't just documentation. They are the single source of truth. Use them to auto-generate type-safe client and server code in Go, Python, or TypeScript. Compare this to REST, where we often write the code first and then try to generate a Swagger file that might or might not be accurate. If the producer changes the data type, the consumer's code literally won't compile. This compile time safety across the network is the ultimate insurance policy for an architect. It eliminates an entire category of undefined is not a function errors in production. But how do these three really stack up when we put them in a head-to-head race? Let's look at the benchmarks that will actually influence your decision. Let's get down to hard data. If we look at serialization speed, gRPC is the clear winner, being significantly faster than REST JSON because it avoids the overhead of text parsing. In terms of payload size, gRPC's binary format is about 30 to 50% smaller than equivalent JSON. GraphQL is the most efficient when it comes to the total network traffic because it eliminates overfetching, but its individual request processing is heavier on the server side due to resolver execution. But there is a massive gotcha browser support. REST and GraphQL work natively in every browser. gRPC, however, requires gRPC Web and a proxy like Envoy to work in a browser, which adds architectural complexity. So the rule of thumb is becoming clear: REST for public APIs, GraphQL for the UI/BFF layer, and gRPC for the high-speed internal backbone. But wait, knowing the tools isn't enough. You need to know how to choose the right one for a specific business scenario. In the next chapter, we're going to put these protocols into a real-world high-traffic scenario and see which one survives the stress test. In a complex microservices mesh, service-to-service communication often becomes the primary bottleneck. Imagine dozens of services talking to each other using standard REST. The overhead of text-based JSON serialization and repeated TCP handshakes can spike your latency to unacceptable levels. Many senior architects fall into the trap of using REST everywhere for consistency, but in a high-traffic internal environment, this is a recipe for performance degradation. This is where gRPC becomes the undisputed winner. By utilizing protocol buffers for binary serialization and HTTP2 for multiplexing, gRPC reduces the payload size and connection overhead significantly. In professional environments, we see gRPC reducing inter-service latency by over 50% compared to traditional JSON over HTTP 1.11. It provides strong typing out of the box, ensuring that services don't break due to undocumented schema changes. However, blindly implementing gRPC without understanding the infrastructure requirements like load balancing can lead to even bigger headaches. But how do we decide when this efficiency is actually worth the complexity? We'll see how to weigh these trade-offs as we look at the broader system landscape. When designing public-facing APIs for third-party developers, the principle of least astonishment must be your guiding star. I've seen many ambitious teams try to expose GraphQL or gRPC to their external partners, only to face massive abandonment rates. Why? Because the external developer ecosystem is built on REST. If a partner has to download a specific compiler just to call your API, or learn a complex query language for a simple GET request, you've already lost. REST with OpenISwagger documentation is the universal language of the web. It provides predictable resource-based URLs, standard HTTP status codes, and effortless integration with virtually any tool or language. Even in 2026, REST remains the gold standard for developer experience because it requires the lowest cognitive load for the consumer. You want your API to be plug and play, not study and struggle. However, sticking to REST for everything can be a double-edged sword when your own mobile app starts struggling with performance. This raises a critical question: should your public API be the same as your private mobile API? Let's look at how mobile clients change the game. Mobile apps operate in a hostile environment of high latency, fluctuating 4G, 5G signals, and limited battery life. In this context, the traditional REST approach of one request per resource is a performance killer. If a mobile screen needs data from 5 different sources, 5 separate round trips over a shaky network will make the app feel sluggish and unresponsive. This is exactly where GraphQL shines as a strategic choice. It allows the mobile client to specify exactly the data it needs in a single request, eliminating both overfetching and underfetching. Instead of the server deciding the response shape, the client takes control. This selective loading reduces the payload size and, more importantly, minimizes the number of expensive network round trips. In professional mobile strategy, we often see GraphQL used as a BFF or backend for front-end layer to aggregate data specifically for the UI's needs. But wait, if GraphQL is so good for the front end and gRPC is so good for the backend, how do we bridge the gap without creating a maintenance nightmare? The answer lies in a hybrid architecture that we'll explore next. The most sophisticated systems today don't choose just one protocol. They use a hybrid approach that leverages the strengths of each. This is typically implemented using an API gateway or a backend for front-end BF layer. In this design, the edge layer communicates with the outside world using REST for third parties or GraphQL for the mobile app. Behind the scenes, that same gateway translates those requests into gRPC calls to communicate with internal microservices. This process, often called transcoding, allows you to maintain a high-performance, type-safe internal mesh while still providing a developer-friendly external interface. It gives you the best of both worlds: gRPC's speed and efficiency in the data center, and REST GraphQL's flexibility and ease of use at the client level. Designing this correctly requires a deep understanding of mapping rules and performance overhead at the gateway. However, as your system grows, you'll encounter a different beast: real-time data. Can these protocols handle a continuous stream of events, or will they crumble under the pressure? Let's dive into the world of streaming constraints. When your system needs to push data in real time, the choice of protocol becomes a matter of fundamental architecture. Many developers confuse GraphQL subscriptions with gRPC's bidirectional streaming, but they serve very different purposes. GraphQL subscriptions are built on top of WebSockets and are primarily designed for event-driven UI updates, like a notification badge or a chat message. It's great for the front end, but it's not a true stream in the sense of high-volume data processing. On the other hand, gRPC's bidirectional streaming is built directly into the HTTP2 layer. It allows for a persistent, full duplex connection where both the client and server can send a stream of messages simultaneously. This is essential for low-latency systems like financial tickers or real-time sensor monitoring. If you use GraphQL subscriptions for high-frequency data, you'll likely hit a bottleneck at the WebSocket management layer. This distinction is crucial for system stability. But what happens when the real-time data isn't just small messages, but massive files or binary blobs? Let's look at the limits of large data transfers. Transferring large amounts of data like log files, HD video, or massive database exports requires a protocol that understands chunking. In traditional REST, you often resort to multipart form data or simple byte range requests, which can be inefficient and hard to manage for very large streams. gRPC, however, treats streams as first-class citizens. It breaks large payloads into small frames at the HTTP2 level, allowing you to send gigabytes of data without loading it all into memory. This binary efficiency is why gRPC is the go-to choice for data-heavy background tasks. Meanwhile, GraphQL is notoriously bad for large binary transfers. You often have to resort to base64 encoding, which adds 33% to overhead or side-channel uploads. In a production environment, using the wrong protocol for large data can lead to out-of-memory errors and service crashes. But even with a good protocol, one question remains. What happens when the sender is faster than the receiver? This is where professional-grade flow control comes into play. As an information management professional, I emphasize that the mark of a senior architect is how they handle backpressure and flow control. In traditional REST over HTTP 1.1, if a server can't keep up with the data, the TCP buffer fills up and eventually blocks the entire connection. In a microservices world, this leads to cascading failures. gRPC, leveraging HTTP2, introduces a sophisticated flow control mechanism. Each stream within a single connection has its own flow control window. This allows the receiver to tell the sender, stop sending data for this specific stream, but keep sending data for others. This prevents a single slow consumer from bringing down the entire communication pipeline. This is the backpressure concept that is often missing from simpler API designs. When you're dealing with high-throughput real-time feeds, gRPC's ability to manage these windows at the protocol level rather than the application level makes it significantly more robust than REST-based alternatives. We've now covered the theoretical scenarios, but the real world is never this clean. In the next chapter, we're going to dive into battle stories, where we look at how these decisions actually played out in high-stakes production environments and where they went horribly wrong. I have seen systems collapse not because of high external traffic, but because of one single malicious query from a legitimate client. Imagine a developer on the front-end team trying to fetch authors, then their books, then those books' authors, and so on, reaching 10 levels deep in a recursive loop. In theory, GraphQL gives clients total freedom. In reality, this freedom is a self-inflicted distributed denial of service. Without a strictly enforced query depth limit, your database CPU hits 100% instantly, while the execution engine tries to resolve deep N+1 problems. This isn't just a performance lag, it's a total system blackout that brings down every other service sharing that database. Many senior architects overlook this because they focus on the flexibility of the schema rather than the vulnerability of the execution engine. But wait, is there a way to let clients keep their flexibility without handing them the keys to destroy your infrastructure? The answer lies in how we calculate the cost of a request before it ever runs. To stop the bleeding in production, we had to implement two critical layers of defense. First, we introduced query cost analysis. Every field in your GraphQL schema must be assigned a weight. A simple scalar like username might cost 1 point, while a nested relationship like followers costs 10 or 20. If the total calculated cost exceeds a predefined threshold, we reject the request immediately. Second, for production environments, we move toward persisted queries. Instead of sending the full variable query string over the wire, the client sends only a SHA-256 hash of a pre-registered query. This effectively turns GraphQL into a type-safe, REST-like endpoint for your mobile apps, preventing arbitrary or malicious query execution. It sounds restrictive, but it is the only way to sleep at night when you are managing high-scale APIs. But GraphQL isn't the only one with hidden operational traps. gRPC has its own set of nightmares that start at the networking layer. When you first migrate to gRPC for internal microservices, you expect massive performance gains. However, many teams soon notice a strange phenomenon. One server pod is melting under 90% load while others are sitting idle at 5%. This is the classic gRPC hotspot problem caused by long-lived HTTP to TCP connections. A standard L4 load balancer like a classic AWS NLB or a basic round-robin will pin a client to a single server for the entire duration of that connection. Unlike REST, where every request can be balanced independently, gRPC requires L7-aware load balancing to distribute individual calls across those persistent connections. We often find ourselves forced to introduce a service mesh like Istio or Linker just to handle this request-level balancing. It is a massive layer of infrastructure complexity that many teams aren't prepared for during the initial performance hype. Does this mean gRPC is too difficult to manage in a modern stack? The second major challenge is the binary black box effect. With REST, you can simply use QRL or look at browser dev tools to see exactly what went wrong. With gRPC and protobufs, the payload is an opaque binary blob that is unreadable to the naked eye. Without specialized tools like gRPC or full-blown distributed tracing with open telemetry, debugging a production issue feels like flying blind in a storm. We learned the hard way that every gRPC service must be designed from day one with interceptors for tracing IDs and structured logging. Furthermore, protobuf versioning is a soft contract. If someone changes a field number instead of a name, your system breaks in ways that are incredibly difficult to trace back to a specific code change. Mastering gRPC is less about the code and more about the surrounding ecosystem of observability and strict schema discipline. Now that we have survived these trenches, it's time to build a structured framework for choosing the right tool for your specific architecture. In the fast-moving landscape of 2026, many architects still fall into the trap of choosing an API protocol based on hype rather than technical requirements. The first critical fork in your decision tree isn't which is better, but who is the consumer. If you are building a public-facing API for third-party developers, REST remains the undisputed standard due to its universal compatibility and the massive ecosystem of OpenAI tooling. However, once we move inside the firewall to internal microservices, the logic shifts. Are you dealing with high-frequency, low-latency communication where every millisecond and byte counts? Then gRPC with its binary serialization is your primary candidate. Or are you building a front-end heavy application with deeply nested, relational data requirements? That is where GraphQL excels by solving the overfetching problem. By 2026, the decision must be driven by the data's shape and the network's constraints, not just what's popular on social media. But wait, what happens when your team's skill level doesn't match the protocol's complexity? I will show you how to navigate that risk in the next scene. Selecting a protocol isn't just a technical choice, it's a commitment to a specific operational lifecycle. In 2026, we categorize these choices by project scale and team maturity. I've seen too many startups suffocate under the weight of a complex GraphQL schema or a protobuf registry when they only had 3 engineers and 5 tables. For a prototype or an early-stage MVP, REST is almost always the correct senior choice because it minimizes overhead. As you scale into a mid-sized organization with dedicated front-end and back-end teams, introducing a GraphQL BFF layer can drastically improve iteration speed. Only when you reach the scale phase, where internal service-to-service communication becomes a bottleneck, should you pivot to the high-performance but high-maintenance world of gRPC. Remember, the most expensive protocol is the one your team doesn't know how to debug during a 2 a.m. production outage. So, when should you absolutely know to use these technologies? Let's look at some dangerous anti-patterns that frequently break modern systems. Let's get real about what actually fails in production. The first anti-pattern I see is gRPC browser without a proper proxy. Even in 2026, browsers struggle with raw gRPC binary frames and trailers. If you are forcing gRPC onto the web without a translation layer like connectRPC or gRPC Web, you are creating a debugging nightmare. Second is GraphQL for everything. Using GraphQL for simple CRUD operations or internal service communication adds unnecessary parsing overhead and schema complexity for zero gain. GraphQL is for the edge, not the core. Finally, REST-only dogma in high-frequency trading or streaming systems. If your services are chatting hundreds of times per second, the text-based JSON overhead and repeated TCP handshakes of traditional REST will kill your performance. Senior architects don't pick favorites. They pick the right tool for the specific traffic pattern. But even with the right protocol, your API can still fail if you ignore the contract. Let's look at how to future-proof your design regardless of the protocol you choose. Longevity in API design isn't about the protocol, it's about the contract. Whether you use OpenAPI for REST protobuf for gRPC or SDL for GraphQL, you must adopt a contract-first approach. This means the schema is the source of truth, not the implementation. In 2026, the most resilient architectures use consumer-driven contracts, or CDC. By letting consumers define their requirements and testing against them, you can prevent breaking changes before they hit production. Are you verifying that your REST responses still match the documented types? Are you managing gRPC breaking changes with protobuf field numbering discipline? Without this checklist, your API is just a ticking time bomb of technical debt. If you follow these steps, you won't just build an API. You will build a platform that survives the next decade of technology shifts. Now that we have the decision matrix, how do we actually put this into action? In our final chapter, I will give you the concrete, actionable steps to implement these strategies starting tomorrow. In the 2026 landscape, the senior architect's role isn't to pick a favorite protocol, but to orchestrate a hybrid protocol mesh. Stop treating REST, GraphQL, and gRPC as rivals. Instead, audit your bottlenecks. If mobile performance lags due to overfetching, deploy a GraphQL BFF. If internal microservice latency is spiking, migrate those high-traffic internal paths to gRPC using protobuf. Keep your public-facing APIs on REST for maximum reach. The true information management professional looks for long-term maintainability and cost efficiency. Map your traffic patterns today. Identify where one-size-fits-all is failing. Real-world systems thrive on pragmatic trade-offs that balance developer velocity with raw performance. Start your 2026 journey by implementing a protocol audit checklist to see which parts of your system are ready for an upgrade. This concludes our deep dive into API architecture. Now go build something that lasts. Payoff. This concludes our series on API design. Apply these frameworks today and you'll see your system's complexity transform into a strategic advantage.